Okay, everybody, we're going to get started. We're working on ideas here within chapter three. Um, it's, I think, a very important class as we try to make it through the ideas within chapter three. Um, I know it's going to be a very active one. I've got quite a few different polls that I want to get your input on and different things that I'm going to be asking you to write or do along the way. So let's get started. So last time when we began chapter three, we looked quite a bit at the information that was in a balanced chemical equation, and we saw that we'd want to be able to interpret that in different ways. Maybe it involved naming, maybe it involved particle representations. But in each of those cases, in all of those cases, we were seeing how the balanced chemical equation was acting like a recipe for us. When we were looking at different types of chemical reactions, the main one that I pointed out that was distinct and we wanted to specifically know the terms was involving combustion reactions. We spent a little bit of time looking at how we could use the periodic table to come up with the formula weight. And we also looked at a little bit of doing conversions involving Avogadro's number and the mole. So I want to begin class here. I've got a couple polls I want to get your information from you on. This is something I'm going to use that's going to set up what we're going to do leading into next week. So I've got a couple different topics here. And for each of these, they have the same format. I want you to respond to a question. I think I can successfully answer questions involving, so first of all, questions involving calculations with isotopes and average atomic mass. Let me send you a poll on that. Is that something you think you would have success with or not? And as always for these, I really appreciate your honest appraisal on this. Um, I'm going to be asking about things that are some skills that we've already talked about, and I'm going to use this information to try to optimize our time as we head into our first exam. So take about 5 more seconds. Okay, let me send you another one. Next one would be same format, but these are calculations involving Avogadro's number. Let me send you a poll on that. So what I'm seeing within this is the data is coming in a wider spread, more students not feeling this is something you've mastered quite yet, which is fine. We're going to talk about it a little bit more this evening, and I'm going to give you some resources you can use for this. Take about 5 more seconds. Okay. Next one within here, same setup. Are you able, do you feel, to classify compounds as ionic, molecular binary, acids, or simple organic molecules? In chapter two, before we can name them, we've got to be able to know the correct classification. How comfortable are you when it comes to classifying ionic compounds, binary molecular acids, and simple organic? Take about 5 more seconds. Okay, that information's helping me. Let me send you one more on the same, within that same format. Besides classifying them as a first step, we have the actual process of naming them. So I want you to think about now your skill. Are you confident that you'll be able to name when it comes to these different formats, these different classifications? How confident are you in your naming skills? for all of these, with the feedback that you give me, I can use that, especially in that strange remote learning environment. I can try to figure out the best ways to get you some resources to support your learning. Just to share this one with you all, this is was pretty typical of the ones where we had a pretty wide spread across different ones. So if for some of these topics you felt that they were not strengths for you yet, you're not alone. Okay, there's classmates within here that are like you, that are identifying a need to continue to work on that. Now, a couple things then as we get started. I mentioned last time that I was going to post within Perusal an optional video that was going to be for extra credit that deals with metacognitive learning strategies. I've already posted that. It's listed as having a deadline pretty much midnight tonight. Uh, about half the students have already gone through within that, and I'm really liking the comments that I'm seeing. I think it's going to be really beneficial. I shared that same information with some students in another section of 1210 earlier in the week. Not that I care about them more than you all, but I think that we'll be able to have a conversation in Perusal that might be better than just sharing the information during class. Couple things that I found within that when I was with this other group. So an important idea within this using metacognition within your learning, there's sort of this model where you want to first begin to review the information. You want to review what you've learned about a topic. You want to then try to answer a question and then give yourself a very honest evaluation. Ask yourself, do you know how to do this? Simply completing something doesn't mean that you've understood it. Ask yourself when you have a question, is this topic easy for me? Would I be able to teach this to a classmate? Could I even prepare my own questions? And if you answer, no, it's not easy for me, I think you need to learn more and then see about retesting yourself and give yourself an honest evaluation once again. This is the core of using metacognition, of using your own brain to determine, well, do I know something or not? Now, when I'm looking at this particular cycle here and I'm thinking about our time together, when I think about strengths of our class, and by our class, I mean the ones that we're setting up together, I know that I'm familiar with the learning objectives for the course. I know what's going to be on your test, and I can provide you with representative questions. I can have you practice things that you can then try to answer and determine if you know them or not. I think I'm also trying to point you to resources to learning more. It might be things that you do before you try to answer a question or in order to improve. I'm trying again and again to point you to different resources, with the e-text being a great one, or maybe different worksheets that I provide. I can certainly give you an overall plan, and I can encourage you to use your metacognition when you evaluate whether you understand something or not. As I think about what can be special with the learning in our class, I think it's these details right here. But crucially, you're the one that does the learning. All I can really do are points here about 1 through 5. After that, it's just up to you to do the learning. And when I say just up to you, I know you can do the learning. I think we've got a good plan to succeed. Now, in every class and in many of the pre-class videos, I try to identify specific questions from the textbook that are going to be relevant for this class. Things that you could use to try to answer the question and then evaluate whether you know it or not. So I'm curious within that. How would you respond to that statement? I've used the questions as a resource to test myself and evaluate my learning. And by the questions, I mean the ones that I provide when I say here's representative questions that are end of chapter questions and the like. Let me send you this as a polling question. Is that a resource that you've used? Take about 5 more seconds. Now, for this next one right here, I want you to pause for a second. I'm not looking for like a 2-word response. I want something a little bit more thoughtful. This is a question I want you to respond to in the chat. If you've not been using this as a resource, can you tell me why? What would you say would be the primary barrier for you that's limited your use of trying to do something like this? Give me a thoughtful response. I'm really curious to learn more. I'm going to give you about 1 more minute if you're still responding, please. Now, one thing that I'm seeing within this, if I were to say a consensus as far as what folks are contributing, if I had to pick out one word, if I were to take the responses here and plop them into a word cloud of some kind, the main thing that I'm seeing within this are issues of time. And I completely understand. I can throw so many resources at you, but I know that you have a finite amount of time to dedicate to this class or to any of your classes. And a lot of you are juggling more things in your world, certainly more than I am in mine. So I completely understand. And one thing I really try to prioritize within this is what is the best strategic way where you can get the maximum amount of learning for the minimum amount of time. I know that you're not looking to waste your time. I'm trying to make it so that the tasks that we are up to are the most on target. And the reason I'm saying that, I think one of the most on target things that you can do would be to try to use the questions that are provided as a resource and see where it falls within your own metacognition. I think by doing that in a targeted way, I think it's one of the best uses of your time. And I say that in part because when I was a guest lecturer the other day in another instructor's course, I came away thinking, man, those students, they are not seeing any representative questions. They are not having any of the information given to them in the same way that I try to say, here's questions that you can then work on. So I'm just saying that I think it is a very strong resource, and I think it would be one that would be something that might be useful as you spend your time. Now, tell me this, going forward, I don't know if I've really sold you on this one or not, and so I'd appreciate your honest opinion on this one. Do you think you're going to use them more or less or about the same going forward? If it was me as they're coming in, one thing I would be aware of is as we've turned to content in chapter 3, we're doing a lot more calculations. And I think calculations are really things that are well aligned with practicing questions. Because I think the feedback that you get tells you very quickly quickly, am I doing this right or not? So as far as the format of the question, what we have going forward and the topics, I think they really set up well to work on, okay? Now, here was some questions as we move on to some content. Here's some questions that were raised in class last time, where we were practicing the skill of can we balance equations with different types of information? Just to point out a couple of these. I would say anytime that you have a question like that, see if you can also use it to practice aspects of naming. So if you have equations like that, I'm sure you could balance those. But could you also then connect this to practice your naming? What I see there is carbon monoxide gas reacts with oxygen gas to produce carbon dioxide gas, or different naming scheme there, dinitrogen pentoxide gas reacts with water to produce aqueous nitric acid. Aqueous, that's what that AQ symbolizes. That means it's something dissolved in water. We're going to do a lot with AQ as a symbol when we get to chapter 4. But I had some questions about, you knew what solid, liquid, gas were. What did that correspond to? Using these to try to build and connect your skills, what I see down there at the bottom, silver 1 oxide decomposes into silver metal and oxygen gas when heated. I'm looking at a reaction like this. This is something that we practiced balancing last time. We begin by writing the different substances. This idea when it says it decomposes, that's a different type of reaction. We talked about combustion before. Decomposition is when we have one substance breaking apart to give us other ones. This would be one that I think would be really easy for you to balance. When we looked at different types of reactions, if I look at that bottom one, what kind of reaction is that? It says we've got this organic molecule, it burns in the air. What does it mean to say burns in the air? They're describing a combustion reaction. So on this slide right here, I think this was looking at the skill of balancing equations, thinking about different types of reactions, being able to connect it to naming. All of those skills are coming together with a slide like I see here. Now, in that same idea of bringing together the ideas, here's some questions that I ask you to try to think about, see if they made sense for you. And I wanted to pick up the answers on these in today's class. So all of these are describing combustion reactions, and they're being connected to naming. And then we're asked to look at it in different ways. So let me step through a couple of these. This one, propane is involved in a combustion reaction. Write out the balanced equation. So I would start out with propane. Propane is an alkane. That's this carbon chain. The propane, the pro part means 3 carbons surrounded by hydrogen. Combustion, it reacts with oxygen to give me CO2 and H2O. My process of balancing this, I'm going to start with a 1 there for the alkane, the propane. That means 3 for the CO2, 4 for the H2O. I'm leaving the oxygen to last because it's all by itself. And in this case, I can balance it just by putting a 5 in there. So I'm returning to that idea. When I'm doing my balancing, I want to leave the thing all by itself for last. Now this one's asking me then, what are the total number of molecules of product for every 1 molecule of propane? So I can get that right from the balanced equation. If I have 1 propane, it looks like I have a total of 7 molecules of product being formed. Here's another one. Hexane's involved in a combustion reaction. Hexane, another alkane, carbon chain with 6, that's what the prefix tells me. So I began to balance it here. I'm leaving oxygen for the last one. Now, if I add up the oxygens on the right-hand side, I get to 19. You know I don't like 19 because it's an odd number. It's not going to help me. So my strategy for that, I'm going to double all of the values. So now I'm accounting for a total of 38 oxygens. I like that better because I'm looking at it in multiples of 2, and it allows me then to balance the whole equation. This one's now asking me to do something with this. If 6 molecules of hexane were used, how much oxygen gas would you need? My balanced equation tells me what happens when 2 combine with 19. This is saying, well, what if you had 6 instead? If I have 6 instead of 2, how would I change this? Well, I'm going to keep the balanced equation the same. I'm just going to look at it as a proportion. My balanced equation's like a recipe. 2 hexanes go with 19 oxygen molecules. That's what the coefficients tell me. So I'm just going to set up something I can cross multiply and divide and figure out how much oxygen goes with that. 2 goes with 19, so 6 must go with 57. I'm just looking at it as a simple proportion. What I've done within this is I've said, okay, I needed to triple the amount of hexane, so I'm going to triple the amount of the O2. That's what I did. I used the coefficients. It was like a recipe. And I don't know, instead of making 1 cake, I made 3 cakes. I tripled the amount that was involved. So I'm just accounting for that with the coefficients. So what I'm beginning to illustrate here is when we have a balanced chemical equation, how we can get information about how the reactants combined with other reactants, their amounts. That's what stoichiometry is all about. Here's another example. This one, we've got several different parts to it. It says methanol reacts with oxygen gas to produce carbon dioxide and H2O. Then there's different things that it's asking to use to interpret that I need to use the balanced chemical equation to interpret. So the first thing is I got to be able to write this combustion reaction. Methanol, that's another simple organic molecule that we want to be able to write the formula for. This is methanol. If they were all hydrogens around it, it would have been methane. I've substituted one of the hydrogens for the OH group to turn it into an alcohol. So this would be methanol. I find within these, when I'm looking at these simple organic ones, it helps me to draw them out. If I draw them out, then I can figure out what the formula is pretty easy. So I'm going to start to balance this one. I'm going to leave the oxygen, the O2 for last. If I look at it right here on the product side, I've got a total of 4 oxygens. On the reactant side, well, I've got 1 within the methanol. And that gets me back to an odd number. 4 minus 1 tells me I have to have a 3. And I can't get to 2 with I can't reach 3 in multiples of 2. So I'm going to double everything. And if I double everything, then I find that I can have the correct coefficient. So what I'm trying to illustrate within these examples of balancing, it began with the name. I needed to write out the components in a combustion reaction. When I did the balancing, I saved the O2 gas for last. And then I ended up doubling terms if I needed to when I had an odd number to accommodate. That's what I was looking at in every one of those examples. Now, let's look at the balanced equation and see if we can answer some questions involving the stoichiometry. How many molecules of carbon dioxide are produced for every molecule of methanol? Well, if I look down here, they have the same coefficients. I see that I have 2 methanols for every 2 carbon dioxides. So how many molecules are produced for every molecule of methanol? Well, it's just 1 to 1. If I had 2 million methanols, I would make 2 million carbon dioxides. It's the same number because they have the same coefficients. How about this next one? If you produce 10 molecules of CO2, how much H2O would you produce? Well, if I look right here, for every 2 CO2s, I make 4 H2Os. I make twice as much. I could set that up as a proportion, but I bet you could do that one in your head. You're going to make twice as much H2O as CO2 because the coefficient is twice as much. So if you produce 10 molecules of CO2, you'd be making 20 molecules of H2O. That's why I keep coming back to thinking about the balanced chemical equation here like a recipe. Last one within the set, we're using the same balanced equation once again. It says that we're starting out with some methanol and some oxygen gas. And it asks, what's in the container after it fully reacts? So I want to, within this one, I'm going to begin with this as sort of a particle level picture where I'm drawing in, or I've cut and pasted 6 different methanol molecules and 6 molecules of O2. And to keep track of what's going on within here, I'm going to touch upon an idea that was in a pre-class video where we're looking at this in terms of what was called a BCA table to keep track of how things are before the reaction, how they change, and what do you end up afterwards. We're going to work through quite a few examples of this next week, and I'm really enjoying and sharing ideas with folks within Perusal on this. Let me just work through one example here, and we're going to work through many more examples next week involving stoichiometry. So first of all, within that setup, the question tells me that I had 6 molecules of methanol, 6 molecules of O2, and I don't have any product there. The reactants are going to react with each other, and in this case, I'm going to find that I use up all of the O2, and I have a little methanol left over. This was the idea of saying, which is the one that you run out of first, and which one do you have left over? And in this case, I would run out of all of the O2 first, and I'd have a little methanol left over. If I look at the values within this change line, well, first of all, I can figure out that I have 2 methanols left over. And I can look to now begin to think, well, what's going to form there? The coefficient for the methanol is the same as the coefficient for the CO2. So if this goes down by 4, this goes up by 4. And the coefficient for the H2O, if this goes down by 2, this must go up by 4. So it's twice that value. And that's what I'm beginning to think about to figure out what's there. Now, I know I went very quickly through this example right here. This is something that I could begin to think about what's in the box before and after. I'm going to continue to explain this idea. I'm going to continue to explain, not as much this evening, but heading into next week, how we use the information in a balanced chemical equation to figure out how the reactants combine with each other, how the products are formed, what are we left with, which one do we run out of first, all of those questions involving aspects of reaction stoichiometry. Like I said, within the videos within Perusal, we're beginning to have those conversations there. But I want to put that idea on pause a little bit. I want to put that idea on pause because I want us to move to an idea in the textbook that's in between those, okay? Stoichiometry is something that we're going to dedicate all of next week to. So I want to make sure that we're skilled at a couple other ideas headed into that. If I look at our progression for where we're going, we spend a little bit of time looking at Avogadro's number and conversions involving mole, mass, and number of particles. And you told me within the poll right at the start that you don't feel like you're a pro at that one yet, which I get, okay? So let me give us an example of that. Let's return to that idea. So we're really, as an important skill, we want to be able to convert between grams and moles by using the molar mass. Within the pre-class video, a lot of students had questions. Well, how do you go back and forth between grams and moles? I use the periodic table and I'm using the molar mass values that are listed there. I'm putting that in a big box because that's going to be a really important skill for us. This idea of using Avogadro's number, 6.02 times 10 to the 23rd, to go back and forth between moles and the number of actual particles that are there, it's less important. I think you'll probably have one exam question like that, but the idea of going between grams and moles, that's a really important idea for us. But let's make sure we're comfortable with using Avogadro's number. So these were a host of questions that I recommended that you might want to give a try to test to see if you knew how to do this. So let me just look more closely at one of these examples. Let me step through this one just so you can see it once again. How do we solve questions like this? So here's that question, 3.42. It says a sample of the male sex hormone testosterone, C19H22O2, contains 3.88 times 10 to the 21st hydrogen atoms. Then it asks different questions about that. So if I'm answering this, I would be setting up dimensional analysis. I'm going to try to cancel my units. So I begin with, what do I know? 3.88 times 10 to the 21st hydrogen atoms in the molecule. If I want to get how many carbon atoms does it contain, I want to cancel the 3.88 times 10 to the 21st hydrogen atoms. I want to cancel the hydrogen atom part. So I can look and see that there are 28 hydrogen atoms for every 19 carbon atoms within that molecule. I'm using the subscripts for that. If I do this and they cancel, it would tell me the number of carbon atoms. How about part B? Really similar. I can first, I can look at it and figure out and cancel the hydrogen atoms by recognizing for every one molecule of C19H22O22, it included 28 hydrogen atoms. I'm again starting with what I know, putting that then in the denominator and canceling out my term from there. The next one, a little bit more extended. How many moles of that would it be? Well, I could start the same way as the example that I just did, but then include a term involving Avogadro's number. That would get me to how many number of moles. What would the mass of it be? Same kind of setup. I could go to figure out how many molecules, what's that in moles, and then I would use the molar mass to get how many grams. This value of 288.4, I just looked at the periodic table and saw the value for carbon, multiplied that by 19, the value of hydrogen, multiplied that by 28, and oxygen, multiplied that by 2. Now, when you look within this one, it gets to be pretty complex by the time we reach all the way down to the bottom. Many of the problems within the textbook are set up this way. They're intended by the textbook authors to show you the process. They're sort of stepping you through to see how do I reach this overall more complex one. So my recommendation on this, if you're trying to practice these, start with the very first step and go A, B, C, D, and see if you can build up to see how they fit together. If you think this is something that you're already good at, see if you can just skip to the very last step. Can you get to the last step without having it build up the pathway to you? So if you're trying to do stuff with Avogadro's number in dimensional analysis, that would be my suggestion. Now, for all of these, I noticed a couple folks saying, well, I'm less inclined to begin doing these problems if I can't easily access the answer. All of the end of chapter questions that we have in our book, all of the questions in our book, our textbook is used by more than 10,000 students every year. If all of those questions are out in the public domain, all of the answers are out in the public domain too. Just as an example within here, I just started typing into the Google machine those first words. A sample of the male sex. As soon as I put the H in there, it finished the rest of the question because people have searched for this so many times. Every end of chapter question we have, every question within the textbook, I would say every question within Mastering Chemistry, it's already out there. It already tells you how to do it. It already shows the answer. So if one of the things that you said you were a little bit hesitant in order to work on these problems because you weren't sure exactly where to get started, I saw some people say that, you weren't sure exactly where the answer would be, any of those, Google will tell you. Soon as you start typing in any of these, it's going to tell you the process that was involved. So you can use that as a resource. I'm just saying, I know it's out there and it's something to be aware of. Now, another thing within here, as far as providing a resource, this idea of how there can be a progression from the more simpler questions to the more complex, I got another resource that I put on perusal that I want to share with you. This is optional, but if you find that you're struggling with the ideas involving Avogadro's number, empirical formulas, and the like, what I'd like you to do is this. So within perusal, what I did, I posted a couple optional documents for sections 3.3, 3.4, and 3.5. I've posted some worksheets. So when you open these up, they're going to be documents. They're going to be files that you can download. If you want to show me your work, what you would want to do within this is at the top of a document, you can designate that you're going to annotate a figure. And when you do that, you just click on it and it puts a little marker, and then you can add a comment, you can ask a question, you can upload a figure to show me your work. I know that you know how to work it when it's in a video. This is how you work it within a document in there. All of these are in the library of perusal. If you just click on that tab, look in chapter 3, you can download any of these. These are all different worksheets from chapter 3 that are in sections 3.3, 4, and 5 that I think are really high quality resources that I stole from my colleague, Dr. Ricardo. I think she has a really good progression within these. And if you want to share ideas within Perusal, I'd love to. If you get stuck on something and you don't know where to get started, shoot me a message. I'd love to share ideas with you on these. The ideas that we have in 3.3, 3.4, and 3.5, they're pretty much overlap with what we talked about last time. Last time we were doing things like formula weights, using Avogadro's number, conversions between molar mass, number of moles. Those are what are in 3.3 and 3.4. 3.5 is something that are some new ideas that I want to share with you right now. So in 3.5, the topic is looking at empirical formulas. Looking at empirical formulas and being able to determine it when we have the data presented in a couple different ways. One way that we want to be able to calculate an empirical formula is when we have information given about the mass of the different elements present. So this says that we have this compound that's in sunscreen. 61.31% of the mass is coming from carbon. About 5 is from the hydrogen atoms, about 10% from the nitrogen, and about 23% from the oxygen. We want to use that information to come up with the empirical formula. If you recall, the empirical formula are the simplest whole number values that we can have describing the different elements that are present. The strategy in order to do this is outlined within the book. If you have the percentages given, assume that you have a 100-gram sample, and now you could think of all of those values not as percentages, but as grams. Then use the molar mass from the periodic table to determine the number of moles of each, and then report that as the empirical formula. Let me step through this example and show you how it's done. So this idea, I took those values that were given in the question, and I'm going to assume I have a 100-gram sample. So that means I have 61.3 grams of carbon. If I look on the periodic table, carbon has a mass of 12.01 grams. That's 1 mole of carbon is 12.01 grams. So that tells me that, okay, you've got 5.015 moles of carbon in that sample. If I look to hydrogen, I'm going to do exactly the same thing. If I look at the periodic table, I see it has a value of 1.01. That's a molar mass for the hydrogen. This will tell me how many moles of hydrogen I have in the sample. And I would do the same thing for the nitrogen and for the oxygen. I'm going to look at the periodic table and find their values. And by doing that, I can figure out moles of nitrogen and moles of oxygen. When I look at the periodic table, nitrogen has a value of 14.01 for its molar mass. Oxygen is really close to 16. So I can now figure out how many moles of each I have in the sample. So I've listed those all right here as the subscripts. Now, this is correct. These are the subscripts that describe the number of moles I have of each, but it's not quite yet how we choose to describe the empirical formula. Remember, with our empirical formula, we want to get to whole numbers, and I'm not at whole numbers right now. Now, one thought within here, a lot of times students get confused. Well, do we use the values for H2, N2, and O2 because those are diatomic, or do we just use the values for the elements themselves? We're just using the values for the elements themselves. In this analysis here, when the values reported for us, it's telling this was the percentage of the mass that was coming from carbon atoms, the percentage of the mass that was coming from hydrogen atoms, the percentage of the mass from the nitrogen atoms. I'm saying atoms in each example. It's not telling me the molecules of those, it's telling me the atoms themselves. So therefore, when we're using the mass values, we use the mass values that we find on the periodic table because those are the values for the atoms themselves. Now, this idea here of coming up with an empirical formula that at this point, I would say is not simplified, I'm curious. Have you seen this topic before? And do you know how to turn this into whole numbers? Let me send you a poll on that. So tell me, Have you seen this topic before? And do you know how to get to whole numbers? So select one or two or neither. Select all that apply. Take about 10 more seconds. Okay, so a lot of folks have seen this before. Smaller, oh, my dog might want to contribute here. My dog's seen it before. A smaller number have the idea of how to get to whole numbers. If you got a strategy for how to get to whole numbers, tell me in the chat. What would you do on this? What would be your approach if you wanted to simplify that? Okay, so I'm seeing a consensus on what I think the best strategy is, and I'm seeing a couple folks bring up what is an incorrect approach, and I think those are both really valuable. Okay, so first of all, let me mention what would be an incorrect approach. I'm probably making some teaching error by telling you the wrong thing. An incorrect approach would be, well, let me just round the values. We don't want to round. When we are done, the values are going to be really close to whole numbers. We don't want to turn 0.728 into 1. We don't want to turn 1.4 into 2 or 1. We don't want to round unless the values are really, really close to being whole numbers. So how do we get them really close to whole numbers? I really like the idea folks were saying of divide by the smallest value. By dividing all of them by the smallest value, what are you going to do? You will turn the smallest value precisely into 1 because you're dividing by itself. And then you'll see what does it mean to divide the other ones by that. And then you can see, are you now really close to whole numbers? So when I divided all of these by the smallest one, okay, now I'm really close to whole numbers. I think my work now is done. It doesn't always work that when you divide through to get to whole numbers in just one step, you're going to be right on the mark. It only works and your work will be done if one of the coefficients is 1. One of the subscripts is 1. But the key step to begin simplifying it, I really like the responses people had of dividing by the smallest one. Now, let me add to this. What we just did was we used the provided values to come up with the empirical formula. The empirical formula is not the molecular formula. Look at this question right here. This is a way that we could begin to think about that. Something has a empirical formula of C3H4. And it also tells me that its molecular weight is 121 AMU. So the question is, well, how do we go from the empirical formula to the molecular formula? If I look at this, if I add up C3H4, I had 12 carbons, 3 carbons, each with a value of 12, 4 hydrogens, each with a value of 1. I got those by looking at the periodic table. That only gets to 40 AMU. The empirical formula can't be the molecular formula in this case. It only adds up to 40. I need to have it add up to 121. So I'm curious, would you be able to use this information to get to the molecular formula? I'm curious. So within this one, would you say you've got a plan, you don't have a plan, or you're not sure? So I'm never sure how these polls are going to go. This poll, I'm absolutely fascinated by the result. It is not at all what I would have predicted. Take about 5 more seconds. Okay, you've really astounded me on this one. You've blown my mind a little bit. All right. Let me show you the results on this. I would have really predicted people would have said you had a plan, you don't have a plan, and very few people would have said not sure. I sort of just tossed that in thinking, well, let me just put it in. Maybe someone's not quite sure. No, I never would have guessed that we would be split between people that say they have a plan or they're not quite sure. So I'm really curious, if you are someone that said not sure, tell me in the chat what you think might work. Okay? Tell me in the chat. If you're a not sure voter, I really want to hear what you're thinking. Do you have a strategy that you're not sure would quite work? What do you think? Okay, so what I'm seeing coming in are folks that somehow are not completely confident in their own decision making, which I get, and people that have a sense of, well, doing something by multiplying it by 3 seems like it might be the right plan. Let's see what's in here. So I appreciate your input. I'm going to say, yes, I do have a plan. And so here's my plan. If you were saying, well, maybe multiply by 3, I think you nailed it. Because if you look within here, the empirical formula adds up to 40. We need to find what multiple of that will add up to a value of about 121. So if we double it, it gets to 80. We triple it, we get really close to that 121 value. And that's precisely what we do. And when I say we triple it, notice that I've tripled both of the subscripts. So it still has the same empirical formula, but now it adds up to the overall molecular weight. So this is how we can turn an empirical formula into a molecular formula. If you tell me the molecular weight, I can figure out what multiple I now need. And a lot of times what you're going to find are these questions get combined. Let me just show you so you're aware of the setup on it. So these are a couple that I grabbed from the e-text. So I really like within the e-text, if this is something you need to practice, how there are sample exercise given, they work through the details, and then after that, they have a practice exercise. And you can just click on your answer and it'll tell you right away if you're right or wrong. So here are 2 practice exercises right on this point. So notice within this first one, cyclohexane, it says that it's 85.6% carbon by mass and 14.4. And then it gives me a molar mass value. And then it asks, what is the molecular formula? Notice this is combining both of the skills that we just worked at. What would I do to solve this one? Pause for a second. You don't need to tell me. Pause for a second. Do you recognize how this practice exercise 1 combines both of the skills that we were just talking about? And would you have a plan? I see percentages given. If I assume that this is out of a 100-gram sample, I know how many grams of carbon and how many grams of hydrogen then it would be. I'm going to look at the periodic table and look up the molar mass for each of those and figure out how many moles of carbon and moles of hydrogen I have. And I'm going to simplify that to come up with the empirical formula. That gets me the empirical formula. Then I'm going to look at the molar mass and see, does the empirical formula equal the molar mass? If it does, I'm already done. If it doesn't, well, then I have to look at a multiple of it to get to the molecular formula. Let's look at practice exercise 2 and see if the same approach works. Exercise 2, I see percentages given. I'm going to assume each of those are grams. I'll look at the periodic table and convert each of those into the number of moles of carbon, hydrogen, and oxygen. I will turn that into an empirical formula. I might have to simplify it by dividing by the smallest value, but I'm going to turn that into an empirical formula. That would be part A. What's the molecular formula? I'm going to look at that and compare and see if the one that I've just come up with for the empirical formula equals the molar mass. If it does, well, then I'm done. If it doesn't, I've got to have a multiple of that. Now, I know as I was talking through these different parts right here, we've combined two different sets of ideas. Tell me in the chat here if you still have a question about either part. The question about the percentages, we're just assuming that so that we can now turn a percentage into a gram amount. And since the percentage is out of 100, let's just assume we have 100 gram present, because that makes it really easy. We can just use those as gram amounts then. Both of these ones here, I think, are really exactly the same format. And by exactly the same format, for each of these examples, we want to, first of all, figure out what the empirical formula is, and then compare that with the given molar mass. I'm seeing within here a question for the practice exercise. I'm seeing a different strategy being proposed right here. I don't think that works. Okay. I think what you want to do is well, let me put it this way, Joey. I'm less clear that it works. I know that the one that I'm proposing is going to be sound and work every time. So I would stick to that one. Okay. Now, let me introduce here a different approach. A different approach because this is describing data that has been collected in a different experiment. The one that I was describing, first of all, to get the empirical formula and perhaps get to the molecular formula with additional information. In that experiment, it's one where the instrument that you use tells you the different elements that are present and the percentage of the mass that they're providing. This is now a different experiment. This is an experiment in an approach called combustion analysis. So I show here a picture of what would be taking place. We know what a combustion reaction is now, right? It's something with carbon and hydrogen. It reacts with O2. It gives me CO2 and H2O. This is the kind of setup that you could do in the lab to do in a combustion analysis. So you put your sample within a furnace. That might be where you put your, wherever you put your alkane. You're not sure what its empirical formula is, but you put the sample within the furnace. It reacts with oxygen that's going through, and then you collect the gases that are produced. You collect H2O and you collect CO2. And what you're going to do is you're going to figure out, you're going to use the information of how much H2O did you collect? How much CO2 did you collect? And you're going to use that to determine what was the original sample that you tested. So combustion analysis, this is another way to come up with the empirical formula. Now, this is one of our more involved calculations within this. It always has the same plan to it. So I want to make clear what the plan is. I know that it's going to have multiple steps. I want to explain, though, what the plan is and show you how it comes together because it's always the same plan. So this would be a typical question. You're testing a sample. You don't know what the subscripts are because that's what you're trying to figure out. You're trying to figure out the empirical formula. So you measure the amount of CO2 that's formed and then measure the amount of H2O. You're going to use this information to determine what were the subscripts. Based on the CO2, you know how much carbon was initially there. Based on the H2O, you know how much hydrogen was initially there. That's why we're collecting the H2O and the CO2. So this is our plan. We'll look at the amount of CO2 that we formed. And by the amount, I mean its mass. We use the molar mass for the CO2 to figure out how many moles of CO2 that was. If we look, then we can see that we have, for every 1 mole of CO2, there's 1 carbon present. So by figuring out moles of CO2, we are figuring out how many moles of carbon were initially there. And we're going to use that to get the empirical formula. We use the H2O very similarly. The mass of H2O is what we collect. The molar mass is 18 grams per mole. That's from the periodic table. That will tell me how many moles of H2O that I produced. We just have to be careful here because we get 2 hydrogen atoms for every H2O molecule. And we need to account for that when we think about how many moles of hydrogen were in the original sample. This step right here would tell us how many moles of carbon were originally there, how many moles of hydrogen were originally there. If we're trying to calculate the empirical formula and it only has carbon and hydrogen present, I think we can now just simplify this and we're good to go. But let me add in another detail. We can also take that information and convert it to figure out how many grams that we had of the carbon and the hydrogen. And you might ask, well, why are you doing that too? You already have moles. We need to do this last step if the analysis has something present besides carbon and hydrogen. Many times it's oxygen. It could be chlorine. Our detectors can only tell us the amount of hydrogen and carbon that was there. It can't tell us about other elements. And you might say, well, could it tell us about the oxygen there? It can't because we're also just pumping oxygen through the furnace. We need that for the combustion reaction. So if we have oxygen present, we don't know if it was in the original sample or if it was something that we added. Now, if you look within this flow chart here, there's definitely several steps. I'm not going to lie to you. There's definitely several steps involved, but it's exactly the same plan every time. So let me show you how it plays out, and I'm sure with a little bit of practice, it's something that you can get. So this would be a very typical question. I've seen this one on an exam before. It says 20 grams of a sample containing carbon, hydrogen, and oxygen is combusted. And it gives us a certain amount of CO2 and a certain amount of H2O. And we're asked to come up with the empirical formula. So let me show you how that flow chart process applies for this. So I listed at the bottom the steps that I would go through. Let's first of all look for the involving carbon. It said that I had 38.28 grams of carbon. I'll use the molar mass to figure out how many moles of CO2 would be produced. CO2, if I look at the periodic table, 44 grams per mole. 1 mole of CO2 includes 1 mole of carbon. So if I take that through, this would be how many moles of carbon were present in the original sample. Carbon is 12 grams per mole, so this would be how many grams that I have. This would be my setup that I'd have right here involving figuring out how many moles of carbon and how many grams of carbon. Take a moment, see if you can write down what would be the strategy here if you're trying to analyze it for H2O. I give you the flow chart right there at the bottom. Okay, I give you the steps. See if you can set up the plan right there. I'll give you a moment to try to do that. The original mass for the H2O was 23.49. See if you can go through and figure out how many moles of hydrogen that was and how many grams. See if you can set it up, and if you got a calculator, see if you can calculate those. I'll give you a couple minutes on that. Take about 1 more minute or so. See if you can set that up, and then I'll show you my work. Okay, so let me show you my setup. So when I say try to set this up, right at the bottom is the flow chart that I'm going to go through. And as you're working on these, when you're first trying to get the hang of it, if you're first trying to learn the plan, there's nothing wrong with having this procedure laid out in front of you. With a little repetition, you're going to know the plan, but there's nothing wrong with having this sort of be your roadmap as you go through. So if I were to look at this one, I have an initial amount of the H2O, 23.49 grams. I need to convert it to moles of H2O by using the appropriate molar mass. 1 mole of H2O was 18 grams. That's also coming off the periodic table. 16 plus 1 plus 1 gets me to the 18. Now I got to be really careful here. That was telling me how many moles of H2O. When I look at the formula, I have 2 hydrogens for every 1 molecule of H2O. So I have a 2-to-1 ratio there. This will tell me how many moles of hydrogen I have. And I can use the mass here to convert it to grams. So within this flow chart going through in both cases, before I go on from there, do folks have questions on those parts? Any question with how we're setting up both of these pathways? Within both of these pathways, I'm just following through the details to figure out how many moles of carbon I had, moles of hydrogen. Grams of carbon, grams of hydrogen. Now, the reason I determined the gram amounts in here, you might say, well, what was the point? You already knew the moles. Because I need to figure out what would be the contribution from the missing component, from the oxygen that's there. My initial sample was 20 grams. I've got 10 grams or so coming from the carbon, 2.6 coming from the hydrogen. Do in your head, does 10 plus 2 equal 20? I don't think it does. There's mass that was still missing. The missing mass is from the element that we haven't measured yet. 10 plus 2 does not equal 20. The missing mass that I have is the one that I'm going to attribute to the oxygen. So the initial sample is said to contain carbon, hydrogen, and oxygen and have a mass of 20 grams. I've accounted for how much was coming from the carbon, how much was coming from the hydrogen, and the missing amount is coming from the oxygen. So now our task is, can we turn that gram of oxygen into how many moles that it is? We sure can by looking at the periodic table. Oxygen has a value of 16. So this would be how many moles that I have left. The moles that I have left, meaning that I would be attributing to the oxygen. So now I've got all 3 values right there. I've got a value for the carbon, moles of carbon, moles of hydrogen, and moles of oxygen. Those are all now my subscripts. Take a second, see if you can simplify that. See if you can simplify this and come up with whole numbers for the empirical formula. When you have values like this, you don't want to say, well, I'll round, it looks close enough. No, we want to divide by the smallest value that we have. When I divide by the smallest value that I had for the one listed for oxygen, let's see how close it comes to whole numbers then. Okay, it comes out really close to whole numbers. Now my work there is finished. And if I were to look, that would be then the choice that I would choose for this one. So this plan right here, if I double back, notice what we did. We had a set procedure to figure out the moles of carbon and grams of carbon, a set procedure for moles of hydrogen, grams of hydrogen. We looked at the difference to figure out how much was coming from the oxygen. And then we just did our usual approach of let's get the empirical formula and simplify it. This set procedure that I show on the slide right here, the one suggestion I have if you're practicing this, it really helps to write neatly because your answers are showing up here along the way. You have figured out moles of carbon and then converted it to grams. You have figured out moles of hydrogen and then converted it to grams. And you end up using those values when you're trying to come up with the empirical formula. I find with it sometimes students, they're going through the steps and they're just writing all over the place. And even though they've already answered one of the parts, they can't find it within their work. So one suggestion I have is if you're doing your writing on this one and you're practicing it a couple times, try to do it neatly so that you can get a clean procedure for it. Let me just show you a couple ways that this is now showing up as far as being able to recognize the problem. So this is one, it's a sample exercise. They work through all the details. This is coming from the e-text. They work through all the details if you want to see it. So it's involving combustion. So right away, what I'm seeing when I'm reading this, it says carbon, hydrogen, and oxygen, and I'm reading combustion reaction. So right away, it tells me this is one where I need to use that procedure for the combustion analysis. And I got to make sure I get the masses because I don't have a direct way to get the oxygen. I'm going to have to get that indirectly. Here's an associated practice exercise. Let's see if we could identify this as it would be that plan as well. So as I'm reading this one, it says it's composed of carbon, hydrogen, and oxygen. Okay, it tells me that it involves combustion. There's an initial mass, and it's telling me CO2 and H2O. Notice this goes on and adds one more detail. It's giving me a molar mass. So we would use combustion analysis to come up with the empirical formula. And then we'd ask that same question. Can we go from the empirical formula to the molecular formula by using the molar mass? We definitely can. So that's adding that skill there of going from the empirical formula to the molecular formula with molar mass, that can sneak into any of these questions. Here's another practice exercise that goes with it. Okay, it looks like here's yet another one where it's telling me carbon, hydrogen, and oxygen. And it's also telling me the molar mass so I could come up with the empirical formula. Once again, within the textbook, all of the practice exercises, the way it's set up is it has a sample exercise that shows you how to do it, and then a practice exercise you can try, and another practice exercise you can try. So this is a really good way to see if you know how to do a skill. Even has a little self-assessment, which is right in that same section to try it again. So if I'm looking with these, I sort of feel like, well, I don't need to give you any more examples. Here's ones if you want to try it that are end of chapter. These are ones where we're trying to come up with the empirical formula. If I look at example C right there, this is not a combustion analysis. This is back to that earlier idea. We've got the percentages. Let's turn them into grams. We use the periodic table and come up with an empirical formula. And then we'll use the molar mass to come up with the molecular formula. There's a combustion analysis set, another combustion analysis set. So one thing that I'll notice as far as where we are at and where we're going, I shared a couple examples about using Avogadro's number, but we've been spending almost all of our time tonight looking at the empirical formula analysis. There's two different types of questions. One is where the mass percent is given and we come up with an empirical formula. that we could turn into a molecular formula if you give me molar mass. The other one is where we're doing the combustion analysis. In that strategy, or in that experiment, we can directly determine the amount of carbon and hydrogen. And if there's something else present, some other component, we get that by difference. Now, when I stack these up, as far as when I look to see how students perform on the exam with this idea of doing combustion analysis, even though it has exactly the same procedure that you can follow every time, it's one of the lowest scoring. I think it's one of the lowest scoring because it takes the longest amount of time. It takes the longest amount of time, but I know that you get better and more proficient with it with practice. I think that these problems involving the empirical formula analysis, these are really good in terms of the feedback, because you right away get information about, did I do this correctly or not? These are all about the practice and the execution. Now, on that point right there, one of the things as far as a barrier that people commented at the start was, when I see a problem, I'm not always sure where to get started. Anytime you get stuck with one like that, send me a message, okay? If you have thought about it deeply, you're trying to figure it out, let's be honest, we're not going to be any smarter 20 minutes later staring at it. So many times, if you are stuck and you don't know where to get started and you have thought about it, you can just send me a message, okay? You're never bothering me. I mean, worst case, I don't get back to you till tomorrow morning, okay? You can always send me a message with that, okay? Many, many times, all I have to do is say, oh, well, remember to balance it first, or start by determining this. There's so many times that I can just get you pointed in the right direction. I don't want you not getting feedback because you're unclear where to get started. If you think it is a legitimate question, meaning a legitimate chemistry question that you are stumped on, I absolutely want to hear from you, okay? Now, when I say I want to hear from you, there's about 5 or 6 people in the class that are extremely willing to send me messages at any time of the day or night with that. And they are getting feedback and pushed in the right direction. I want you to be one of those people too. So if you find that you're not sure how to get started, just send me a picture of your work. Show me where you're at, and I will absolutely be able to point you in the right direction. All of the stuff that we've been doing here with empirical formulas, notice that when we're trying to determine the empirical formula, we don't have a balanced equation. We have information about the masses that were involved, and we use that to come back to get to the empirical formula. We don't have a balanced equation when we're trying to determine the empirical formula, because we don't know the subscripts for something. When we have a balanced chemical equation, that's all about now applying ideas in stoichiometry. So the stuff that we're talking about tonight, for the most part, when we were looking at empirical formulas, we didn't know how to get, our task was to come up and determine the subscripts. When we're looking at stoichiometry problems, those begin by having a balanced equation. So that's when we can use things like dimensional analysis or a BCA table to get our answer. When we are doing stoichiometry problems, we're interested in how we have particular amounts of products and reactants being formed or being left over. We have questions about, well, which of those do we run out of first? How much were we expecting to get versus how much do we actually get? All of those are questions pertaining to stoichiometry. Strategies that we can use with that, within the video, I introduced 2 different approaches, something called dimensional analysis, which we've already seen when we were doing conversions involving like the metric system, and an approach called the BCA table, which stands for before, change, and after. A lot of people within the video had questions like, well, which one's better? Do I have to use one or the other? Which one do you like to use? Let me tell you my perspective on that. Back in the day, when I was your age, I only heard of dimensional analysis. I used dimensional analysis in high school. I used it in college. I don't know. I didn't have to use it in grad school because we didn't do questions like this. But I used it my entire life until I became a teacher. And about 15 years ago, I was introduced to this approach using a BCA table. It was when I was working with high school teachers. And initially I saw it and I was a little skeptical. And I'm like, well, I already know how to solve these with dimensional analysis. But I thought about it, I tried it, and I am now 100% converted to BCA tables. And that's not just in my own teaching, that's in my own thinking. If you give me a stoichiometry problem, I am always going to use a BCA table. I just am. I know that it leads to a higher success rate. I can see everything in front of me and I can sort of check my work as I go along. So if you have the question, well, which one should we use? Do they both work? They both work. But if you are not a pro at dimensional analysis, please give BCA tables your full attention. I think they're going to be superior for you. If you already have a great strategy using dimensional analysis, cool. I'm not going to try to upset that. But if you are learning the process of stoichiometry or relearning it, if you do not feel like you're a pro with dimensional analysis, please give my discussion in the video of BCA tables your full attention, because I think it's going to win you over. Now, when I look at where we're going within this chapter and beyond, I put in a really bold line here, stoichiometry. Stoichiometry is going to be the largest topic that you have on your first midterm exam. It's going to be the main idea from chapters 1, 2, and 3 that we use the rest of the semester. When I look at these different types of questions on your exam, you're probably going to have all of these different types. I would say probably a quarter of your test is going to be different aspects of stoichiometry. So I was trying to set things up so we'll have a real clean run at that idea next week. A real clean run. That's why I had you begin to look at BCA tables with the pre-class video. And it's something that we're going to pick up, and I'm going to work many examples in our class on Tuesday, because I think it's going to be I know it's the most important topic that we're going to have heading into the exam. And we're going to have a really good opportunity next week to make sure that we're really confident and master that. Once again, folks, I really appreciate your attention. I'll hang around if you have questions. Let's keep it moving.